Welcome everybody at the second day of our conference, Water and Innovation, Water Technology. Well, I think some people are still asleep. Yesterday we had a nice dinner at Krasnapolski, so that was a little bit late, but I think more people will come. Yesterday we spoke about membrane technology and biological processes. Today we will speak about sensor technology and water and ICT, but the first session is about emerging substances and emerging technologies. And this session will be chaired by Alex van der Helm. And Alex van der Helm is researcher at Waternet, and he is also working at Delft University Technology. Alex, the floor is yours.
Well, I don't have very much to add. Jan-Peter gave the session. I'm glad even around 25 people even showed up in this early hour. Regarding the dinner in the Krasnapolski yesterday evening was really nice. It's really a very nice building. Also for the foreign guests it was nice to see. I would like to invite our first speaker, Mr. Hardy Temmink. He works for the Wageningen University in the sub-department of environmental technology, and he works at wetsus.
Nee, goed, dat werkt.
Ja, daar richten op de paal.
Okay. Thank you very much. Good morning to you all. Okay, my name is Hardy Temmink, but this work that I'm going to present has mainly been conducted by two PhD students, Hernández, Leal, and Marten de Graaff. And as you can see by the colors, Lucia worked mainly on so-called grey water, and Marten worked on so-called black water. What I'm going to do is I'm going to show you a bit how micropollutants, and then I mean personal care products, as well as pharmaceuticals, behave in grey water and black water treatment systems. And this is important, we think. We promote this very much at wetsus and at Wageningen University because we believe in decentralized treatment of wastewater. For the exact reason you can see here in this slide. Black water if you use vacuum toilets, and then by black water this scheme is not entirely correct. I noticed this morning in the train, because this is black water, is from the toilet, but here you also have separated urine. But what we mean by black water is the combination of urine and feces. And officially the separate streams are called brown water and yellow water, as far as you can speak of officially, of course. So when I talk about black water, I mean the mixture of urine and feces from the toilet, so toilet water. And we also promote collection of this toilet water by vacuum toilets, and that produces around 7 liters per person per day, and grey water around 95 liters per person per day, and grey water is all the water coming from the laundry, the shower, etc., etc. So the relatively clean water. And if you look at the distribution, you can see that the organic load is distributed evenly, roughly, among black water and grey water. Phosphorus is mainly in the black water, and nitrogen is even more present in the black water. So this offers opportunities to recover energy from the black water and the nutrients from the black water, and then reuse the grey water for several purposes. Now, this is a demonstration project in Sneek, which is in the north of the Netherlands, and around 32 households are connected to a grey water and black water system. And the black water treatment is in the garage of one of the inhabitants of this area. But we collected the brown water and the black water and the grey water and transported it to our labs to do all kinds of experiments. Now, this is black water composition. This is from a monitoring session of around 3 years, which confirms that, of course, which confirms that the COD is very high. If you calculate it theoretically, it should be around 25 to 30 times as high as in sewage. So that's you can gain energy from it, and also the nitrogen and the phosphorus concentrations are relatively high. Now what we did is we treated this black water in a system consisting of an anaerobic reactor, in this case USB, then an autotrophic nitrogen removal unit. We were not recovering the nitrogen because we had this rule of thumb that if you have nitrogen below 5 grams per liter, it's useless to recover it and you should simply remove it. It's a different case if you work with urine, for instance, then you're above this 5 grams per liter and then it's worthwhile recovering it. So we removed it autotrophically obviously because we already removed the organics and transformed it into methane as an energy source. And then after the nitrogen removal, we recover P, and that's all we do. We didn't look at the removal of micropollutants, we just looked at the behavior of micropollutants in this system. Now, if you look at the performance of such a black water system, then I focus a bit on energy because I think it's important to share that with you. If you look at the black water system, you could recover this amount of energy, that's in megajoules per person per year. And if you compare that for the full treatment line of conventional wastewater treatment plants, you lose around 107 megajoules per person per day. So you have a net energy gain from a black water system, which is around, it's not a lot, it's around 5 to 10% of your electricity consumption in your household, assuming that you use around 3,000 kilowatt hours per year. So this is, in terms of energy, a very interesting system. Now, if you look at the treatment performance, it's not as good as a sewage treatment plant, which is obvious, but if you look at the loads, then the loads for COD, nitrogen and phosphorus are lower than the loads that are discharged from conventional WWTPs. So the concentrations are much higher, but the load is lower. Now, micropollutants. And in the case of black water, we're talking about pharmaceuticals. Now, in black water, they are theoretically around 25, 30 times higher than in sewage. That's one thing. They are only partially removed, as far as we know, in wastewater treatment plants. The risks are very difficult to assess, and several effects were reported. Now, well-known effects are this feminization of fishes by ethinyl estradiol, and also by Prozac, for instance, in the United States, a reduced freshwater mussel production. So there are some worries, and therefore we decided to start monitoring these pharmaceuticals in black water systems. Now, we had some selection criteria, which are quite logic, I suppose, that they have potential harmful effects in the environment, reported effects, the consumption, removal in wastewater treatment plants, and we decided to look at several therapeutic groups. Now, these are the compounds we looked at for the black water system. So we have an analgesic, paracetamol, 2 beta blockers, antihistamine, some antibiotics, some anti-inflammatory compounds, steroid hormones, and an antileptic compound. And I'm going to summarize the results in this graph. These are concentrations from left to right. This is, for instance, for paracetamol. This is in the black water. And all compounds were detected in the black water, apart from the hormones, strangely enough. And this is from the anaerobic reactor to the partial nitrogen removal reactor, and then to the effluent. Now, the concentrations were not 25 times sewage concentrations, which is not surprising, because we only looked at 32 households. So there's quite some fluctuation and differences between a bigger system. Only 3 compounds were not detected, apart from the hormones, in the effluent of the whole treatment line. Those were paracetamol, tetracycline, and doxycycline, which are antibiotics. Now, you could conclude that you need physical chemical treatment because all the compounds are still present in the effluent, but that's of course risk dependent. We don't know. We know that these compounds can be removed quite well by ozone, activated carbon, even nanofiltration. Whether it's really necessary, I cannot say. Now, then we look at grey water, same procedure more or less. We want to use reuse grey water after sufficient treatment for several purposes. And therefore we treated this grey water in 3 different biological systems. We had a aerobic reactor, we had an anaerobic reactor, and we had a sequence of an anaerobic and an aerobic reactor, all operated at the same hydraulic retention time. Now, if you look at the performance in terms of COD removal, so organic removal, then the aerobic system behaved the best, as you could expect maybe. The anaerobic system, to our surprise a bit, behaved not that good. And probably this is linked to the presence of anionic surfactants, which inhibit the anaerobic treatment process. Now, the in grey water you have a huge amount of personal care products. If you look at your shampoos and the bottles and other products that you use, you can see there's a huge amount of different compounds. We selected quite a bit of those, I think about 18 compounds different. For the same selection criteria we also used for the pharmaceuticals, more or less. And this is the list of compounds we looked at. We had a couple of preservatives, parabens, many UV filters, some fragrances, some surfactants, biocides, and a plasticizer, bisphenol A. That's what we looked at. I can tell you, by the way, that we hired a Finnish postdoc for 2 years to help us set up all the analysis, because that's a huge effort if you want to do it in a proper way, and it's really, really very difficult to do. Just as a warning if you want to start similar research. Now, this is the presence of all these compounds in grey water. Apart from 2 parabens, all the compounds were detected in the water. Surprisingly, maybe nonylphenol is also present in the water, although it's restricted in the EU. So what we suspect is that it's in a textile imported from, for instance, Asia, and then when you wash your clothes, it gets distributed to the grey water. That's what we suspect. We can't be sure. Also, this concentration is very high. This is a UV filter. And galaxolide also is quite high. This is a fragrance. Now, this is a summary of what we observed when you looked at removal, anaerobic and aerobic removal. These are a couple of compounds, just example compounds. Only 2 compounds had a removal efficiency of above 85% in all different treatment systems, so both anaerobically and aerobically. There were 14 compounds which were not removed anaerobically, but were removed aerobically. So aerobic treatment in terms of removal of these micropollutants is the best. And 5 compounds, among them PBSA and tonalite. Tonalite is a fragrance and PBSA is a UV filter, were not removed at all. Now the removal efficiency, aerobic removal efficiency, focusing in on aerobic removal, seems quite high. Most of them above 80% at least. Only this one, which is a UV filter, PBSA also a UV filter, and also tonalite, where their removal was not very good. Effluent concentrations, now that shows a similar picture, of course. This one, EHMC, is quite high in the effluent, and also PBSA and galaxolide and tonalite were quite high in the effluent. Now, what does this mean in terms of risk? Well, the answer is we don't know. Sorry, I forget something. We also treated the grey water by ozone and activated carbon. And what we saw is that those are suitable techniques. These are ozone experiments. This is the ozone dose, cumulative ozone dose. These are concentrations of the compounds. And what you see is you would need like 10 to 50 milligrams per liter of ozone to remove these compounds. And all were removed quite well, apart from PBSA, which is removed but requires a bit higher ozone dose, apparently. Now, it's important to realize the ozone dose is not determined at all by the micropollutants. Those concentrations are very small, but by the background dissolved organic carbon in the water, which is around 16 milligrams per liter in our case. Yeah, so the background TUC determines the ozone dose. So also determines the costs, which would be around 0.05 to 0.20 euros per cubic meter, if you want to accomplish this. Activated carbon, we had many results. Now, within 5 minutes, the micropollutants are gone. If you mix it with powdered activated carbon, they are gone. No problem at all. But we also used these granular columns, granular activated columns, and we saw a similar good removal, but we also spiked these columns with micropollutants at elevated concentrations. And in this case, this is after 3,000 bed volumes of treated water in the system. And by that time, the column was completely saturated with organic carbon. And then we decided to spike it even further with PBSA, just to check the efficiency of the system for a compound. And you see there's still an additional 2,000 to 3,000 bed volumes you can use the column for without significant breakthrough of this PBSA. So that's good news in terms of a lifetime of carbon for these micropollutants. Now, risks. We did not do a lot of risk analysis. We tried to check the literature on these compounds, on these grey water compounds, these personal care products. It's hard to find information. What we did is we took the grey water, we checked the concentrations of several potential estrogenic compounds, and we added up from literature for these compounds the estrogenic potency in 17 beta estradiol equivalents. And what you then see is if you compare it to sewage, for instance, you see that grey water is much lower in this potency. If you treat it anaerobically, it doesn't change a lot, which matches the removal of the compounds that we saw, the chemical data. But if you treat it aerobically, you go down a lot in this estrogenic potency. Now, for tonalite, we found a no observed effect level of 3.5 micrograms per liter. And we have in our treated grey water 1.5 microgram per liter, so it's already close. Now, if you have this compound, which is a UV filter, we have a predicted no effect level of 0.4 micrograms per liter. In summertime, we saw very much higher concentrations of these UV filters than in wintertime, which makes sense, of course. In summertime, it can be as high as 23 microgram per liter, so it's a lot above this predicted no effect level. But of course, there are unknown that we're not aware of, non-detected compounds in this water. We only analyzed 18, and we don't know anything about the effect of mixtures of these compounds. Oh. We also did, together with the University of Amsterdam, some in vivo tests with Daphnia magna and Hieronymus riparius larvae. Now, it showed that grey water has an acute toxicity. If you have biologically treated water, and then I mean aerobically treated water, it eliminated mortality but still affected the growth of these organisms. If we applied ozone and activated carbon, it completely removed this acute toxicity, and we even saw some stimulation of growth of these organisms. Now, what's next? We only looked at the water. We didn't look at the sludges. If you treat grey water and if you treat black water, you're also producing sludge, and you want to do something with the sludge. So we're now also looking into the sludge matrices to analyze the compounds in those matrices, which is a difficult job. We think it's important to develop easy in vitro bioassays for all these different functions of these micropollutants. We do that together with our Department of Toxicology of Tinka Merck. She's working on that. We want to link the concentrations to the responses of these tests. And finally, we want to use this information, perhaps, to develop cheaper and more specific technology to remove these compounds. Thank you for your attention. The questions are right now or
No.
later on? Okay.
We'll proceed with the next presentation, and afterwards we will have time for discussion. I already see some nice links between the presentations we're gonna have today, so it's also good for discussion if we hear all the presentations first.